Hi, I'm Isuke Hirota. Today I'm going to talk about our RCCV 2025 paper, Bias in Gender Bias Benchmarks, How Spurious Features Distort Evaluation. First, let's talk about the background. Large vision language models, which are trained to understand both images and text, have a significant problem with gender bias. For instance, studies have shown that they tend to associate certain jobs like doctor with men and nurse with women. This is a critical issue that hinders their safe deployment. As shown in these figures, the standard approach to measure societal bias is using datasets containing real-world images with gender labels. But this leads to a fundamental problem. These benchmark images are taken from the real world, so they often contain spurious correlations. That means non-gender features, like the objects or background, are unintentionally linked to a certain gender. For example, women might appear in kitchens more often and men outdoors more often. This brings us the core question of our research. Do these spurious features distort our gender bias evaluations? As illustrated in this causal graph, we want to know if the model's output is truly influenced by gender, which is Z to O, or if it's being influenced by spurious features, B, which are themselves correlated with gender, G to B, creating an indirect parse, G to B to O, that confirms our measurements. Our methodology has two main steps. First, we confirm the existence of spurious features in widely used benchmarks. We do this by training classifiers to predict a person's gender using only isolated features from the images, just the colors, just the lighting, just the objects, and just the background. As you can see in the table, for color, objects, and background, the classifiers achieve accuracy significantly above the 50% across all datasets. This confirms they are indeed spuriously correlated with gender. Next, to measure the impact of these features, we perform controlled interventions. We take the original images and perturb one feature at a time, as shown in the examples here. We shift hues, change brightness, mask out objects, or blur backgrounds. Then we run the bias evaluation on both the original and modified images. A large change in the bias score after a small perturbation indicate that the model is highly sensitive to the feature. To quantify this impact, we introduce a simple metric called delta. Delta represents the relative percentage change in the bias score before and after we perturb a feature. A large delta values means that the model's bias score is highly dependent on the specific non-gender feature, suggesting the initial bias measurement is unreliable. Let's look at the results. We evaluate several large vision language models, including LLaVA and QN2VL. This table shows the delta values, where darker red represents a larger delta, meaning the model is more sensitive to that feature. Weak middle strong mean the strength of the feature perturbations. As you can see, perturbations of objects and backgrounds consistently have the largest effect. In some cases, a very minor change, like masking only 10% of objects, causes the measured bias to swing by over 175%. This strongly suggests that the model's evaluation is not just about the person's gender, but is heavily dependent on these spurious contextual cues. The visual examples further confirm that feature perturbations can completely flip model predictions. For example, model's response to "can this person become a salesperson" changes from no to yes after background blurring. Finally, these spurious features can completely flip how we rank models in terms of fairness. This graph shows bias rankings under increasing object populations. Look at the blue line, QN2VL. It starts as the least biased but quickly becomes one of the most biased. This shows that current benchmarks can reliably tell which model is fairer. Here's a quick summary of our findings. For more details, please check out the paper.